Welcome back. In the second part of this lecture, we'll be talking about the algebraic ways in which we can solve an inequality where it's a polynomial or a rational function. So for this idea here, we basically have to remember how things work when we're thinking about graphing, which is if you're a polynomial, then the places where you change from being below the x-axis to being above the x-axis would be at your x-intercepts. So for polynomials, the real important points for us would be those x-intercepts. Those would be the places where you can change where you are from above to below, or from below the x-axis to above. When it comes to rational functions, there's a couple of things which can make us switch direction or switch location from above the axis to below. If you have a vertical asymptote, that's a place where maybe you could be changing your direction from being above the x-axis to being below it. Or, of course, just as it was for polynomials, intercepts would be places where you can change direction from above to below the x-axis. So that's our idea here, that the only places where you can change signs from positive to negative or from negative to positive would either be at a root or at a place where the function is undefined, at holes or vertical asymptotes. So the idea here is that first we'll start by, as always, rewriting our inequality so that it's got 0 on one side and everybody else on the other. And then we'll find all of the roots and all of the places where our function is undefined, all the places where the denominator is 0, if we've got a rational function. And then basically the idea next is plot those numbers on a number line. And because let's say you found for some polynomial that it crosses the x-axis at 1 and at -2. Well, then there's really three places to look at. There would be the values that are less than -2. There are the values between -2 and 1. And then there are the values that are larger than 1. In each of those regions, you'll either always be entirely above the x-axis or always below. So the only thing you really need to do then is, once you've set about putting your roots and your places where your rational function is undefined on the number line, you'll split up your number line into regions, just as I've got here 3 separate regions. You'll need to pick a test point inside of each of these 3 regions and ask yourself, does that make your function positive or negative? And then, based on your answers from this number line, we'll be able to then state our solutions for that algebraic, for that inequality. This is something that's maybe harder to describe in words than it is to actually do. So let's actually do a couple of examples here where we solve an solve an inequality rather, algebraically. So for the first one, we want to solve where this rational function is greater than 0. And it's already got everybody on one side with 0 on the other, so far so good. I'm just going to write out here just so I can name this. I'm going to name this rational function f of x. Because there's going to be a point towards the end of solving this where I'll need to evaluate this rational function at different values of x, so nice to have a name for it. Okay, so the first thing that I'll want to do is to find out where are the zeros, where are the places where this is undefined, and of course you would do all of that by factoring. So factoring the numerator and factoring the denominator. And so you find that if you're looking at this rational function, you can see that it has zeros or x-intercepts at 2 and at 4. And you also can see that there should be 2 vertical asymptotes for this rational function. You have vertical asymptotes of x equals 3 and x equals -3. So that means that we've got 4 important points, 4 important x values, 3, -3, 2, and 4. And so what we'll do now is take those 4 values and draw them on a number line. So next thing that I'll do is draw myself a number line. And it doesn't have to be perfectly to scale. I'm just drawing out a line with my values of x, the -3, the 2, the 3, and the 4. And you can see that that takes our real number line and splits it into several chunks. There's the values of x that are less than 3, the values of x between -3 and 2, values of x between 2 and 3, between 3 and 4, and the values of x that are greater than 4. So in each of those regions, we're going to select a value for x, a test value, and find out what would be the y value for our function. So any x value in the interval works. If you're looking at the first interval here, which is all the values that are less than -3, you could choose whatever value you'd like as long as it's less than -3. But choose conveniently. I mean, if you want to choose a number, choose a nice number. In this case, -4 seems like a reasonable choice. You could choose -7,000,000,005,000,000 if you want to, but eventually what we're going to need to do is come up with what our y value is, and our y value we would find by putting -4 into our function. And so you would have to then go back and remind yourself of what your function is, and evaluate what is that when x is -4. And so I've done all of the calculations already, and I found that when x is -4, the y value was 48/7. So that means that in this region here, in the part that's to the left of x being -3, we are above the x-axis. We have that in this region, our function is greater than 0. And then we can do the same thing with all the remaining regions. So between -3 and 2, I picked a test value of 0, and I found out that the value for f of 0 was -8/9. And so that meant that f of x is negative in that region. And you could do the same thing between 2 and 3. I pick 2.5. The y value is 3/11, and so we are above the x-axis. For between 3 and 4, I picked 3.5. And the y value when x is 3.5, that was -3/11. So in this little interval here between 3 and 4, f of x is negative. It's below the x-axis. And then finally, for the last part, when we're to the right of 4, I chose an x value of 5. And we can find out what f of 5 is by putting 5 into our function. And our function has a y value of 3/16. So in this interval here, f of x is greater than 0. So what we were interested in for this function would be all the places where f of x is, where this function is greater than 0. We were looking for where is f of x above the x-axis. And so for this then, where are we above the x-axis? Well, we're above the x-axis when we're to the left of -3. Also between 2 and 3, and also when we're to the right of 4. So for my solutions, everybody to the left of -4, not including the everybody to the left of -3. I wasn't reading carefully here. Try that again. There we go, better. -4 was my test point, but the interval goes all the way up to -3. The second interval which was all the values between 2 and 3. Again, not including the 2, not including the 3, because we're looking for where is it greater than 0. So we're not interested in where are you at the x-axis, we're interested in where are you above the x-axis. So we have everything up to -3, everything between 2 and 3, and then the last interval would be everybody that's to the right of 4, together with everybody to the right of 4. So that's basically our idea here, that when we're solving an inequality algebraically, we'll first find out if it's a polynomial, where are the zeros? If it's a rational function, where are the zeros, where are the wholes, where are the vertical asymptotes? Next, we'll put those points on a number line, and then in each of those little intervals, select an x value, and then find out what the y value is for our function. And then based on that, we'll draw our conclusions as to where is our function positive in this case. That's what we were interested in. This also is useful too if you're thinking just on the graphing side of things. If you did want to graph this rational function, you now know where it's above the x-axis and where it's below. So that actually gives you some extra information if you were thinking about doing things graphically. All right, let's do another one. And so for this one, it's not already written with everybody on one side, so that's the first thing that I would do, is move everybody to the one side of the inequality. And so for this one, my function f of x that I'm talking about here would be that x to the 4 minus 8x squared minus 9. Okay, and we're interested in where is this greater than or equal to 0. So the first thing that we would have to do is factor this out. And so you might notice that this is one of those functions that looks like a quadratic, sort of. It's a disguised quadratic. If you were to let u be x squared, then u squared would be x to the 4. So you could factor it in that sort of a way using that technique. So refresh that back in chapter 1 if you want to have another look at that. The idea is that once you've done that, it would factor out as x squared plus 1 times x squared minus 9. The x squared plus 1 won't factor any further, but the x squared minus 9 will. It'll factor as x minus 3x plus 3. So we want to know, where is this polynomial? Where is it at the x-axis or above it? Where is it greater than or equal to 0? And if we're looking at this polynomial f of x, we can see that it has only 2 zeros. The x squared plus 1, that doesn't actually give us any zeros, because that would be where x is plus or minus the square root of -1, and of course that's not a real number. So there's no solutions that comes from that first bracket. Only from the second and the third. From the second bracket, we'll get the 0 that x is 3, and from the next one, we'll get that x is -3. So for our zeros, we have x is 3 or x is -3. So now all we need to do is just get ourselves a number line going. And so there we go. On our number line, we'll only need to put in those two numbers, the -3 and the 3. And we'll just need to pick test points on either side and in between. We'll need to pick a test point for something that's less than -3. We'll need to pick something between -3 and 3. We'll need to pick something that's larger than 3. And we'll need to find out what our y value is for our function. Just as one little aside before I do this, one thing that you might notice, and this is, again, all the stuff that we learn about our functions gives us extra hints and gives us extra clues which can make our life easier. You might notice, if you were to check this, that f of x happens to be an even function. And that's actually kind of useful here, because one thing that we'll know would be that since it's an even function, that means that f of -x should be the same thing as f of x. And I mention that because if you're looking at my intervals that I'm interested in, I could pick a test point in the first interval of -4. I could pick a test point in the second interval of 0. And I could pick a test point in the last interval of +4. And this is where my fact of this function being even is helpful. I know that f of -4 and f of 4 should actually be equal to each other. And in fact, you can confirm this, that if you put in -4 into your function, you get a y value of 119, and that's the same as the y value you get when you put 4 into your function. You also get a y value of 119. So if you notice that this is an even function, then automatically once you've figured out what the y value is when x is -4, then you've also figured out what the y value is when x is +4. Of course, if you don't notice that the function's even, that's fine. You can still go ahead and come up with your correct conclusion just by picking test points and checking them out inside your function. So we know what f of -4 is and f of 4. We still need to know what f of 0 is. And f of 0, that would be -9. So we were looking for, back in the original part of this question, where is this function? Where is it greater than or equal to 0? Where are we at the x-axis or above it? Well, it looks like we are above the x-axis when we're less than -3, and we're above the x-axis when we're greater than 3. In between -3 and 3, we're below the x-axis, so we won't include that. And we are at the x-axis at -3. We're also at the x-axis at +3. So for my solutions, everything up to and including the -3, together with everything from 3 onwards, including the 3. So for this one, my solutions would be everything up to and including -3, and then everything from 3 onwards. All right, so just a couple more to go here. For this one, your first move that you might be tempted to make, and I have the question here that says you might be tempted to begin by clearing out your fractions. You might say, well, why don't I just turn this from being two rational functions, one rational function minus another, why don't I just clear out all the fractions by multiplying everybody by x minus 1, x plus 1? And I ask, why is this a bad idea here? Now, the reason why it's a bad idea is actually because of this, because of the fact that we're talking about an inequality. If you were looking to solve where is x over x minus 1 equal to 6 over x plus 1, then feel free. You could go right ahead. You could multiply both sides by x minus 1 times x plus 1. You would have to keep in mind that you do have some excluded values. You would have to remind yourself later on that 1 and -1 are excluded, that you can't have x being either of those two. So if you were trying to solve it by clearing out the fractions, that would be the only little caution there. But remember that when we're talking about solving an inequality, that when you multiply both sides by something, the inequality might change direction depending on whether what you're multiplying by is something positive or something negative. Now, since we don't know when x minus 1, x plus 1, when that's positive and when that's negative, then we don't know yet when this should be changing its direction. That's the reason why we're not going to be clearing out fractions here. If you multiply both sides of an inequality by something involving x, it's possible that your inequality might have to change directions if what you're multiplying by turns out to be something negative. And so since we don't know when that thing is negative or positive, then we are not going to multiply both sides by that x minus 1, x plus 1. Instead, what I'll do is I'll bring that 6 over x plus 1 to the other side, so that I have everybody on one side now less than or equal to 0. And I'll make common denominator, multiply that first fraction top and bottom by x plus 1 rather. And for the second one, multiplying it top and bottom by x minus 1. And then the only thing left for me to do is then simplify this numerator and then factor it. And so if you were to take the x times x plus 1, multiply that out, take the 6 times x minus 1, multiply that out, then do the subtraction, the first thing minus the second, that numerator would simplify to give you x squared minus 5x plus 6. And we want that to be less than or equal to 0. And so that's where x minus 2 times x minus 3 in the numerator over x minus 1, x plus 1 is less than or equal to 0. And you can see here that there's two x-intercepts, the zeros at x being 2 and x being 3. You can also see that we have vertical asymptotes here at 1 and at negative 1. So vertical asymptotes x equals 1, x equals negative 1. And so that is then the numbers that we're going to be putting on our number line. Our function, the f of x that I'm going to be using to evaluate here, that will be this function that we have over here. That's my f of x. You could either have it in the factored form or the unfactored form when you're evaluating. It doesn't really matter, but I'll write it in the factored version that we have here. F of x, that's x minus 2, x minus 3 over x minus 1, x plus 1. Okay. And so now the next thing that I'll do is I'm going to just add an extra page here. There we go. And draw myself my number line. And I'm going to put on my values. I had vertical asymptote at negative 1 and at 1, and x-intercepts at 2 and at 3. And so the only thing left for me to do here is to now pick those test values, pick those values that are less than negative 1, between negative 1 and 1, bigger than between 1 and 2, between 2 and 3, and then larger than 3. So let's do some test values. I'm going to select x being negative 2, so that's something less than negative 1. Between negative 1 and 1, 0 is a good choice. Between 1 and 2, 1.5 is a good choice. Between 2 and 3, 2.5 is a good choice. And larger than 3, let's go for 4 is a good choice. And then you can find out what your values are. At negative 2, the y value is 20 over 3. At 0, the y value is negative 6. At 1.5, the y value is 3/5. At 2.5, the y value is negative 1 over 21. And when x is 4, the y value is 2/15. So of course, this went fast for me because I already did these calculations in advance. For you, when you're doing these, you'll have to, of course, do the calculations of putting in negative 2 into f of x and finding out what is the y value, then doing the same for 0, then doing the same for 1.5, 2.5, as well as for 4. So we are interested in, and just going back here, we are interested in where is our function f of x, where is it less than or equal to 0? So where are we at the x-axis or below the x-axis? And if we're taking a look at what we have, we can see that we're below the x-axis here between -1 and 1. We are also below the x-axis here between 2 and 3. That's the other place where we're below the x-axis. We're also at the x-axis at 2 and at 3. If we go back, remind ourselves that 2 and at 3, those were the zeros, those were the x-intercepts. 1 and -1, on the other hand, those were not x-intercepts, those were vertical asymptotes. We would not be going through x being 1 or x being -1, which means that when we're stating our solutions, between -1 and 1, we are definitely below the x-axis. We won't include the -1 or the 1 because both of those are vertical asymptotes. Neither of those are values that we can put into our function. And together with, we'll also have all the values between 2 and 3. We will include the 2 and we will include the 3 because those are places where the function has a value exactly 0. That's where we're exactly at the x-axis. So our solutions, everything between -1 and 1, and everything between 2 and 3, including the 2, including the 3. All right, so one last one here that just sort of feels like a random question that has nothing to do with what we've done so far, but it actually does. Here it's a question of find the domain of this function, and the reason why this actually fits in this section is if you're looking for the domain of this function that involves a root, remember that we know that for roots the inside needs to be 0 or larger. So in other words, if you're looking for what is the domain of g of x, you're looking for where is the inside of that square root 0 or larger. So there we go. We're solving a polynomial. We're solving a rational function inequality yet again. Do the same thing as we always do. Factor. And this factors relatively easily. And you can see that you've got vertical asymptotes at 2 and at -2. And you've got zeros, you've got x-intercepts at 1 and at -1. So that means that when we're drawing our number line, we'll have several points to put on it. We'll have -2, -1, +1, and +2. One other thing just to mention here, before we do our calculation, I'm just going to name this. I'm going to call this f of x. That's my x squared minus 1 over x squared minus 4. One thing that you might notice about this, yet again, that this is an even function. F of x is even. So actually that will save us a little bit of work if we notice this, because if you're looking at the test values that we might want to pick, a test value below -2, we might choose a value of -3, and we're going to need to find out what is the y value at -3, and that turns out to be 8/5. But if we've noticed that our function is even, then that means that when x is +3, the y value should also be 8/5. Similarly, for between -2 and -1, I chose an x value of -1.5, and I found that the y value at -1.5 was -5/7. And because it's an even function, that means that for x being +1.5, we should have the same y value, which should also be -5/7. And then for my last test point, I picked between -1 and 1, I picked a value of 0, and that gave me a y value of 1/4. And now what we were interested in was where is f of x? Again, where is f of x positive or 0? In other words, where is it at or above the x-axis? And we've already found some of the answers here. We know that it's positive in this interval to the left of -2. It's positive in this interval between -1 and 1. It's positive in this interval to the right of 2. So that's part of it. And also, where are we at the x-axis? We need to remind ourselves that 2 and -2, that those were the locations of vertical asymptotes. We weren't at the x-axis at either of those places. It was at the zeros at -1 and 1. That was where we were at the x-axis. So if we're looking for where are you positive or at the x-axis, our solutions would be everybody up to, but not including -2, together with everybody from -1 to 1, including the -1, because that's an x-intercept, including the 1, because that's another x-intercept, and then together with everybody larger than 2, not including the 2, because 2 is where we've got a vertical asymptote for that rational function. So that means then that the domain for g of x is exactly what we had up above, is exactly all of that. Because remember that where you're solving for where is that rational function greater than or equal to 0, so in other words, when we tried to solve where is this rational expression greater than or equal to 0, that's asking the question of where is this function, root of that rational expression, where is that defined? And that's defined, as we said here, for values of x that are between far left up to -2, together with the values between -1 and 1, including the -1 and the 1, together with the values that are larger than 2.